All right. So we're going to have two recordings. I accidentally pressed the wrong button. I pressed stop recording. So most likely there'll be two recordings for this lecture. So we're just going to continue on with the part two of this lecture. So let me go ahead and share my screen. We're still on chapter 4. We will probably readjust the due dates, but you know, when you see this, if you're asynchronous, this may have already been readjusted. I was a little ambitious, I think, with my thought process for today. It's good to be more optimistic than pessimistic. Initially, I thought we'd get through both chapter 4 and chapter 5 today, but we're not going to be able to do that. I guarantee that. And I want to make sure that I did. Just wanted to make sure my audio is turned on. We saw this. This was a previous slide that we just looked at. So sources and use of alkanes. Gasoline is a mixture of straight branch and aromatic hydrocarbons, all produced from oil. So you have these, you have upstream oil refineries where, they're going to get the oil out of the ground. Then you got, midstream and downstream, you have the oil processing, such as like Sasol or CP Chem. And then they give this product to someone like Procter & Gamble or 3M, where they can turn it into a product. So you have these different processes, in the petroleum industry. And some industries do all three. Some industries, get it out of the ground. Then they have to refine it at these refineries. Then they send it off by usually rail or some other type of transportation boat to get it to the next place. So you have a single bond rotation resulting in multiple 3D shapes called conformations. That's what you're seeing right here. There are various ways to represent the 3D shape of a compound. Newman projections are ideal for comparing the relative stability of possible conformations resulting from a single bond rotation. So, all this stuff is the same stuff. The only difference is this is this kind of represents the whole thing right here. So it's basically it's ethane, right? And with ethane, they're showing, okay, this hydrogen's here, this one is right here, and this one is right there. And you can imagine, this bottom one right here, I'm going to designate this one as an X. This is X. Oh, that's not an X here. This one will be Z. And this one will be, what should I call this one? U. I kind of showed you, where they are on that Newman projection. And while you're looking at that, I need to find my watch. And rethinking this, I think we're gonna go on to chapter 4 homework tomorrow. I thought chapter 4 and 5 were gonna be much quicker than what we are doing. So we'll do chapter 4 homework tomorrow. And then we'll go on to chapter 5, if we have time, and then we'll start the chapter 5 homework, next week. So I'll readjust the homework due dates accordingly. So we'll see where we are tomorrow. And then, if we get done with the homework, we'll just keep the due date for chapter 4 the same, but we'll obviously push chapter 5 homework the due date. And you can imagine, let's just say we had a bunch more carbons in here. And let's just say we had it as 6, hexane. Well, hexane would have 1, 2, 3, 4, 5, 6. And then we're still looking at the same stuff, but all this stuff in between it would be this stuff going this way. So hopefully that makes sense. And then you'd have, I'm going to get my eraser out because I want to. Actually, I want to draw this really, really good. I'm going to draw a 6 carbon chain. I'm going to basically do the same thing for ethane, but it's going to be 6 carbons. We're going to have 1, 2, 3, 4, 5, 6. So in the 6th position, I'm still going to have these blue ones, but I'm going to start designating A. We'll call this one B. We'll call this one C. We'll call this one, I guess we'll keep with it, D. We'll call this one E. We'll call this one F. So let's start labeling them where they come. This HA, this is your back carbon right here. So this is your back carbon. I didn't do the best project this, but let's just call this one HC here. This one might be my HB. This one might be my HA. And this one right here, you have to kind of rotate these things, but let's just call, this one, D, E, and F. And we have all these carbons in between, this would be 1, 2, 3, 4, 5. So what I wanted to show you is we're not seeing 2 through 5 because 2 through 5 is in that projection right here going this way, right? So all we're looking at would be carbon C1 and then C6. So basically we're showing C1, C6, and this is this new in projection. You can see in the Newman projection, the carbons in front have this line right here, right? The carbons in back, they're behind the circle, aren't they? Okay. So they give us an example. Let me see if they have another example. No. So you're looking down here. So we're looking here. Let's just call this one. This is going to be in the front. This is going to be in the back. What they don't show you is there's 2 hydrogens here, right? Likewise, you have another hydrogen here. So this methyl group right here is right here. This chlorine here is here. And that hydrogen right there is this right here. This methyl group is here, followed by these, they're the same hydrogen, so here and here. Those hydrogens in the front are equivalent. So does anyone have any questions on how to draw that Newton projection for this? So even though this would have been, 1, 2, 3, and this would be propane, right? In the one position we have a chloro group, in the one position we have a methyl group. So it'd be 1 chloro methyl propane. But to draw the Newton projection, you drew it like this. So the angle between atoms on adjacent carbons is called a dihedral angle or a torsional angle, and it's 60 degrees in the molecule below. If you go another 60, you get to 120. If you go another 60, you get to 180. And you keep on going around, you get to 360. And sometimes they can be eclipsed. What do we mean by eclipsed? Should have drew that right here. I mean, this would be the eclipse. And I show you the eclipsed right here. And eclipse, why is it highest in energy? Because these are going to really repel each other right here. They're being really close, so it's going to repel each other the most. So that'd be the highest in energy. This is the most stable conformation right here, because they have that they're further away from each other. They're not eclipsed on top of each other. So this is the same molecule. It's rotating, but this molecule would prefer to be in this conformation. It's more stable because there's not as much torsional strain. So here they're showing you the same molecule. Everything's the same molecule. They're just rotating. What they're doing right here, they're rotating the hydrogen. So here they're keeping the hydrogen on the backside. This is the backside hydrogen. They're keeping this the same. The only thing they're doing is they're rotating this right here. See, they're rotating it down. They rotate it over and back to the same position. This is your staggered position. Here's your eclipsed. And they're keeping that that back hydrogen in the same position, and they're just rotating this one around. So let's just call this one 1. Here the ones are here, and here the ones in that position. And this is higher in energy. Due to the torsional strain. And this strain is relieved here. So the strain is relieved in a staggered position. It's also due to the electron pair repulsion between the eclipsing bonds. So 99% of the time, this molecule is going to be in the staggered position for ethane. So that means if we go back to these, to this graph right here, 99% of the time, it's going to be here. With the other 1% here. So even though it has a single bond and it can rotate, really due to the electron repulsion, it's going to be set in that staggered position. And here they said the difference in energy can also be rationalized by the presence of stabilizing interactions in the staggered conformation. We can see that overlap, that side-by-side overlap between the sigma bonding versus sigma anti-bonding. I think this is really for, in all honesty, for like an inorganic course to look at these molecular orbitals. Now they're looking at the torsional strain for propane. Now we're not looking at ethane, right? We're looking at propane. This has 3 carbons. And you can see the difference between the torsional strain is 14 kilojoules per mole. And for ethane, it was only 12, I believe. Yeah, it's 12. And the reason why we add that 2 kilojoules per mole extra is because we add that extra methyl group. So we have that extra methyl group right here. That's going to add that 2 kilojoules per mole. So it's going to be even more stable to be in this staggered position once again. Let's see something. I think I can change the color. Yeah, I can. Blue and whatever. That's a good idea. Just have it black. Hey, talk about this, what we've already mentioned. So if each hydrogen-hydrogen clipping interaction costs 4 kilojoules of mole stability, that total can be subtracted from the total to calculate the contribution of a methyl hydrogen eclipsing interaction. So here 4. I actually prefer red. Yellow is a little. 4, 4, until you get 8 right there, and take 14 minus 4, 8 is 6. Does the analysis of torsional strain for butane shows more variation? Note there are multiple staggered conformations and multiple eclipse conformations. So we went to butane now. And there's going to be multiple staggered conformation, multiple eclipse conformations. So you may ask yourself, well, why is this one 19 versus 16? Because in this eclipse, we have 2 methyl groups. And there's more just, if you have a methyl group and a methyl group, there's going to be more, sterics and electron repulsion is the word I was looking for. Whereas here, I should draw that as CH3 and here, if we have a CH3 and a hydrogen, it's going to be a little lower. You can see there's a 3 kilojoule difference right here between 19 and 16 is 3. So the most stable is to actually put the methyl groups on the opposite ends right here. Even in the stagger position, when we had the methyl groups, close by each other like that, it's 3.8. So if we just call this as a baseline, there's a 3.8 difference right here. 3.8 kilojoules per mole difference between the methyl groups right here versus them opposite each other. And that's due to the electron repulsion. And I have names for this. So when the methyl groups are farthest apart, that's called the anti. When the methyl groups experience a gauche interaction, they're right next to each other. And we saw this in the previous example. So now, since we know this, let's erase all this stuff. This would be anti. Here's your gauche. And what's the difference between this conformation and this one? 3.8 kilojoules per mole for butane. So the anti position will be 3.8 kilojoules per mole lower, so it's more stable. It says the highest energy conformation for butane results when the methyl groups eclipse one each other, and we can see that right here. So the methyl-methyl eclipsing interaction accounts for 11 kilojoules per mole of energy. So this is kind of a summary right here. It says the energy cost for eclipsing gauche interactions can be used to approximate the energy of a given conformation. So like I said, you don't have to memorize this stuff. You can use this for your exams. I wouldn't expect anyone to measure specific numbers like this. So ideal bond angles for an sp3 hybridized carbon. That means we just have really single bonds. So if cycloalkanes are flat, each carbon in the ring would experience angle strain. So also if a ring was flat, then all carbon-carbon bonds would be in eclipsing rotamers, causing considerable torsional strain. But that's not the case, because what happens is with this six-membered ring, it kind of relaxes into a boat conformation. So that's what happens right there. It's not all on the same plane. I can't even draw it all on the same plane very good. I'm not the best drawer, but the six-membered ring is not all on the same plane. And I'd have to twist it. It relieves itself by going to that boat conformation, or that chair conformation. Sorry about that. Like that. That's how it relieves its strain. It says the combustion data for cycloalkanes show that a six-membered ring is the most stable ring size. Right here. So if we go ahead, increases, and if we go below, it increases. Not that at 12, though, it starts going back down. Cyclobutane is 27 kilojoules per mole less stable than cyclohexane. Can't really see, you know, maybe this is 681, and I guess if you go 27 below that, I mean, let me see. Maybe this one's at 654, something like that. Slight torsional strain results because adjacent carbon-hydrogen bonds are nearly fully eclipsed nor fully staggered. And you see this is puckered right here. You know, for the 6-membered ring, remember I drew the chair conformation. Now, if we drew it, you know, as a flat planar, this would be 120 degrees right here, right? But when we draw it in this puckered conformation, it relieves strain. So we're relieving strain. That means it's going to be more stable. I should get rid of that. So we're relieving strain, and it's more stable. A cyclopentane is only 5 kilojoules per mole less stable than cyclohexane. Very little angle strain. If we go back, so there should only be about 5 kilojoules per mole between them, and you can see that right here. Let's there's only 5 kilojoules per mole difference right here. And slight torsional strain adopts an envelope conformation to avoid most of it. So we call this an envelope conformation. This one here was called puckered. And this is stuff that just has to be memorized. You know, I don't like memorization, but a lot of organic chemistry does come down to memorization. You know, so just practice it. So the bond angles, what they're talking about right here, are nearly 109.5 degrees. And where do you see 109.5 degrees at? Remember this right here? These angles are 109.5. So that means these are nearly tetrahedral. Nearly tetrahedral. That's what that means. And this will be the last slide that we do today. So they're talking about cyclohexane, you know, and what is the most stable conformation of cyclohexane? We've mentioned this already, that it's the chair conformation. And these other conformation, and why is the chair conformation the most stable? Let me see if I can draw this real quick. It has to do where the hydrogens are located at. See, the more that they become eclipsed on each other, I'm going to try to do my best. You know, the more you know, repulsions it has, it's not going to want to stay in this conformation right here. So it all has to do with how the hydrogens are located within that cyclohexane to how much repulsion you're going to see. All right, so that's it. I think we've done enough today. I'll stop sharing the screen.